Hello, this is Hilary Weller. In this video I'm going to describe the finite volume method for linear advection. Finite volume is a very general technique. It's a class of methods. There are lots of different finite volume methods. I'm going to describe the entire class and give a couple of trivial examples. So with using the finite volume method, volume integrals of predicted variables are made rather than predicting the quantity of phi itself. So if we've got a linear advection equation to predict phi, with a finite volume method we'll predict the volume average or the volume integral of phi over after the domain is divided up into little volumes. We'll calculate the volume integral of phi by calculating the amount of phi that is entering and leaving each cell over all of the faces. So I've got the rate of change of the volume average of phi is equal to the sum over all of the faces multiplied by the flux. So Fi is the flux, the amount of phi entering and leaving over each face. Fi is the flux over through edge or face I. The finite volume method can also be derived by discretizing the flux form of the advection equation. So constant density flow is divergence free, so div u is equal to 0. So two forms of the linear advection equation are equivalent. We've got the advective form with d phi by dt plus u dot grad phi is equal to 0, or the flux form d phi by dt plus the divergence of u times phi is equal to 0. So if we discretize this flux form, or the conservative form, using Gauss's divergence theorem, we'll get, we're just discretizing the advection term. So div of u phi, we're going to take the volume average, so 1 over volume times the integral over the volume of the divergence of u times phi. And now we apply Gauss's divergence theorem to this integral, and so we convert it into an integral over the surface area of the volume. So rather than integrating over the volume, we integrate over the surface, which is around the edges of the volume, and the divergence in here becomes phi multiplied by u dot ds, where ds is the outward pointing normal to the surface S. So at this point it's exact, and then if we write this as so this is u dot ds multiplied by phi, it's the velocity in the outward pointing normal direction multiplied by phi. That is the definition of the flux over the flux over each face. So that's 1 over the volume multiplied by the sum of the flux over the faces. And again, at this point no approximation has been made because we assume that we know the fluxes over the faces exactly. So this volume has surface S, and ds is a vector pointing outwards normal to the surface. And then the flux is defined as phi multiplied by u dot ds, so that's velocity in the direction of the surface normal. That's the flux Fi over edge I. One of the advantages of the finite volume method is that it's conservative. However you use it, you'll conserve the variable you're advecting. Because there's a lot of freedom in how you calculate this flux Fi, but however you calculate it, you'll get the same amount if you estimate flux to move the mass or quantity of a variable from this cell to this cell. The same amount will be subtracted from this cell as is added to this cell. So exactly what leaves one cell will enter another. So it'll always be conservative. So there are numerous ways of calculating this flux F from surrounding values of phi and the velocity. Now we're going to look at the finite volume method in one dimension. We're going to assume that u, the velocity, is constant. So for constant u, the fluxes are estimated at positions in between, at the edges of grid boxes. So it's u multiplied by phi at the edge. So if we're discretizing the finite volume sense, we've got phi in the grid boxes, phi j plus 1, and then the edges of the grid boxes are denoted by the j plus a half and j minus a half. So to discretize the advection equation with the finite volume method, we get d phi by dt at position j is equal to minus u phi j plus a half minus phi j minus half over delta x. So the rate of change of phi here is equal to that value minus that value divided by delta x. And that's how it is discretized with the divergence theorem. So it remains to work out how to estimate phi j plus or minus a half from the surrounding values of j. So we could do some simple approximations. So for example, we could choose phi j plus a half is equal to half of phi j plus 1. So this value is just half of the surrounding values. If we use this approximation, so this centered approximation, and if we assume that the time derivative is discretized using centered in time, we would recover exactly the centered in time, centered in space finite difference scheme. Similarly, if we choose forward in time for the time derivative, and if we assume that phi j plus half is always going to be equal to phi j, so this value here is always going to be equal to this one, assuming that this value is upstream, then we'll recover the forward in time, backward in space finite difference scheme. You should try to demonstrate these yourselves with solutions on the lecture version of the notes. Another thing that you can do with the finite volume method is you can solve equations on arbitrary meshes. And for example, this is a mesh of the sphere, just looking down on it on the North Pole.